Hi guys, today we are going to learn about chapter 2, which is atomic structure. Okay, so this is the question. This diagram shows the patterns of lines in the Lyman series of the atomic hydrogen spectrum. Okay, so Lyman series represents ground energy levels equals to 1. Okay, so based on this diagram, what we could saw is here has the biggest distance between this line, right? And when moving towards the right, the distance actually is decreasing. So the distance actually represents the wavelength. So when you look at the distance, this has the largest distance, right? So this would be the first line. And this will be the second line. So what we know is the formation of first line in Lyman series will be n equals to 2 to n equals to 1. This shows that electrons drop from energy levels 2 to energy level 1. Okay, and same as this, if this is n equals to 2 to n equals to 1, this will be 3 to 1. And this will be 4 to 1, 5, 6, and 7. Okay. So the first question is, which part of the electromagnetic spectrum is the Lyman series found in? Okay, so this question actually we cannot find the answer from the diagram above, but this is actually testing some knowledge. Okay, so for Lyman series, the answer will be ultraviolet region. Okay, so let's recap back all about the other series. What is their spectrum region? Okay, so for Lyman, it's actually ultraviolet. And for Balmer, it's actually visible. Okay, so please take notes. For Balmer series, the questions actually will be like this, okay? Would you expect to see the light corresponding to this spectral line in Balmer series? Okay, so the answer will be, yes, I can see the light corresponding to this spectral line because the spectrum region for Balmer series is visible. Therefore, we can saw the line, okay? Balmer series is actually the most frequent questions asked for the spectrum region, okay? So take notes. And for the other three, which is Paschen, Brackett, and P-Fan. These three has the same spectrum region, which is infra. Okay, infra. Okay, so let's move to the second question. Why does the series consist of a number of individual lines rather than a continuous spectrum? Okay, so for this question, it's actually asked about the formation of line spectrum. Okay, so the answer will be like this. Electron will absorb energy and is promoted to a higher energy level. Okay, so basically it was like this. For example, here is n equals to 1. When the energy absorb energy, electron absorb energy, it will move to a higher energy level. Okay, so for example, it moves from n equals to 1 to n equals to 3. Okay, so at this situation, the electron is in the unstable state. Okay, is in excited state and it is unstable. Okay, therefore it will release energy. When it releases energy, it actually drops back. Okay, drops to a lower energy level, and this energy is in the form of light, or also known as photon. Okay. Therefore, it forms line spectrum like what we could saw in this diagram. Okay, in this diagram, okay. Then we just transfer the diagrams that I draw just now into sentence. So electron absorb energy and is promoted to a higher energy level. When the electron is at the excited state, it is unstable. So it will drop from higher energy level to lower energy level, and the energy is released in the form of light. We can also write photon, which corresponds to certain wavelength and frequency. Therefore, line spectrum is produced. Okay, so the next question is calculate the lines in the Lyman series which has the lowest energy of light. Okay, highlight this lowest energy of light. So lowest energy of light actually represents n equals 2 drop to n equals to 1. Okay, the electron, okay, is the electron drops, not the energy level drops. Okay, so the electron will drop from n equals to 2 to n equals to 1. And we can use the formula of E equals to Rayberg's constant n initial square minus n final square. So this is the formula we use. Don't forget to write out the formula because the formula actually got marks, okay? This 1 marks, okay? There you substitute all the values. Okay, so for Rayberg's constant, it has two different values, okay? The first value is for calculating the wavelength, and the second value, the energy. Okay, so for calculating the wavelength, it will be 1.097 times 10 to the power of 7, and the unit is n minus 1. As for energy, it will be 2.18 times 10 to the power of negative 18 joule. Okay, this is the point. Joule and meter. So when you want to calculate the energy, remember to use this formula. And if you wanted to calculate wavelength, please use this, okay, this value, because it uses the unit of meter, and this one uses the unit of joule. Okay. So for this question, it wants to find energy. Therefore, we use the value of 2.18 times 10 to the power of negative 18. Then, okay, so out of this, one to the power of, this is initial, right? So the initial will be n equals to 2 square, and the final will be 1 because it is the Lyman series, and the answer will be negative 1.635 times 10 to the power of negative 18 joule. Don't forget to write the units, because if you don't have the units, then your answer is wrong. Okay, second question. Iron is the sixth element in transition elements. Use an orbital diagram to describe the electronic configurations of valence shells of the atom. Okay, so in this question, we need to find the proton number of Fe first. So the proton number of iron is actually 26. Then you write out the electronic configuration first. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Okay, so this is the electronic configurations for Fe26. And for the valence shell, is actually this one. Okay, 4s2 and 3d6. And the question 1 orbital diagram to describe the electronic configuration of valence shell. Just draw. Okay, 4s. 1, 2, 3d. Okay, so 3d has 6. 1, 2, 3, 4, 5, and 6. Okay, yeah, so this is the answer. Second question, predict the most stable ion for Fe. Okay, so for most stable ions, is actually Fe3+. So why? Okay, so what we could solve from here, this is the valence shell, right? When we remove 2, we need to remove from the outermost shell, which is 4s. Okay, so we remove this first. We actually remove 2 electrons, right? Remove 2 electrons. Okay, so it left 3d6, but actually 3d6 is a partially filled orbital. You see, this is not fully filled, right? But we can remove 1 more electron from here. When we remove this electron, it actually forms like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 3d. So this is actually a half-filled 3D orbital and it has extra stability. Therefore, we remove total. Here remove 1, right? Total will remove 3 electrons. That's why it forms Fe3 plus electron. Okay, so the answer will be like this. Fe3 plus. 1 mark. Half-filled half-filled 3D orbital has half-filled 3D orbital more stable than partially filled orbital. Okay, so the last question, write a set of quantum number for the highest energy orbital. Okay, for highest energy orbital will be 3D, okay, not 4s, okay, because according to the Aufbau principle, the orbital is arranged according to the energy. Okay, so what we could solve from here, 4s is actually has the lower energy than 3D. Okay, so the highest energy orbital will be 3D orbital. Okay, so write set of quantum number. Set of quantum number will be N, L, M, S. Okay. Then you write N equals to 3. L equals to N minus 1. Could be 2. It could be, okay, wait L, it could be 2, 1, or 0. But highest energy orbital is 3D. Okay, so 3D will be, this is S, P, D, F. Okay, so for S is actually 0. L equals to 0 represents S orbitals. So 1 will represent P, 2 will represent D, 3 will represent F. That's why we need to write 2, because it is a D orbital. Okay, so for M, you could write anything, okay, plus minus L. Okay, so you can write 1, you can write 2, 1, 0, negative 1, or negative 2. It depends, okay. S is actually the most simple one, whether you want to write positive 1 over 2 or negative 1 over 2, okay. So that's the end of my videos. Thank you.